Hello everyone and welcome back to the channel. In today's digital world, speed is everything. Whether you are browse a website using a mobile app or streaming content, you expect things to be fast and responsive. But what makes some applications feel incredibly snappy while others lag behind? One of the most powerful and widely used techniques behind high performance systems is caching. Today, we are going to explain caching and talk about what it is, why it is so crucial, different strategies, and challenges involved. If you want to understand how systems deliver data in lightning fast speed, you're in the right place, I guess. So let's start with what is caching. Let's start with fundamental definition. Caching is a technique used to temporarily store copies of frequently accessed data in high-speed storage layers, such as your computer's RAM, which is a random access memory. Think of it like keeping the most common used tools on your workbench instead of having to walk to the toolbox every single time you need them. The primary goal of caching is significantly improve system performance by reducing latency, the delay in accessing data, offloading work from the main data source like your primary database, and ultimately providing much faster data retrieval. How this is happening? Okay, let's just take an example. Let's say that we have our application. Okay, let's say that we have a client and the client sends a request to our application server. Okay, and the server fetch the data from the database. Okay, and the database sends the data the server wants to fetch back, and it will be sent to the client. This process is okay. It's not bad. It's working well. Everything is smooth. However, we might go through a problem that it takes some times because databases often are on disk and they have I/O operation. They are not that fast. So if we use the cache system, basically we will store the frequently accessed data in in-memory storage, which is way more faster than the database storage by itself. So when the client wants to, like, let's say the client wants to retrieve a product, so it will try to ask the server, and the server will get the product directly from the cache if the cache has a product. If the cache doesn't have the product, we call this a cache miss. The server will fetch the product from the database and store it in the cache for future use and return to the client. By using cache, first we are improving the responsiveness of our application. Also, we're reducing the load on our database because all the frequently accessed data will be served from the cache or not from the database. So yeah, let's talk about why we use caching. The impact of implementing a good caching strategy is profound, and it's quite essential. Let's try to understand why. First, improved performance. This is the most obvious benefit. By storing frequent access data in a fast cache, the time required to retrieve data is significantly reduced. Instead of going all the way to a slower disk-based database, your application can often get what it needs from the much faster cache. Number two, reduce load on backend systems. Caching acts as a shield for your primary data stores. It reduces the number of requests that need to be processed by your backend databases or services, freeing up their valuable resources for other critical operations. This means your database can focus on handling writes or more complex queries. Okay, next, increased scalability. Because caches handle a large number of read requests very efficiently, they make your entire system more scalable. Your application can serve more users, and more requests without needing to immediately scale up expensive backend infrastructure. And next we have cost efficiency. This is direct consequences of reducing backend load. By minimizing the work your primary database and servers have to do, caching can help lower overall infrastructure costs, especially in cloud environments where you pay for usage. Lastly, enhanced user experience. At the end of the day, it's all about the user. Faster response times due to caching lead to a much better, smoother, and more satisfying user experience, which is particularly critical for web and mobile applications. Okay, next we want to talk about where can data be stored, or let's say the types of caching, where data can be stored. So caching isn't one size fits all solutions. It can implement at various levels different forms. Let's explore some of them. Number one, we have in-memory cache. As the name suggests, in-memory caches store data directly in the server main memory, which offer extremely fast access. These are typically used for things like session management, keeping user login information readily available, storing frequently accessed application objects, or acting as fast front layer for slower databases. Popular examples include, I guess, Redis and Memcached. Number two, we have distributed cache. When you are dealing with large-scale systems that span multiple servers, a distributed cache becomes essential. It ensures that cache data is constantly available across all different nodes in your distributed systems, providing an unified caching layer. Example, I guess, including Redis cluster, which distribute Redis data across multiple nodes, and cloud services like, I guess, Amazon Elasticsearch. Elastic Cache. Elastic Cache, not Elastic. Number three, we have client-side cache. Caching can also happen on the user's device itself. Client-side caching involves storing data directly on the client, typically in the form of cookies, browser local storage, or application-specific caches. This is very commonly used in web browsers to cache static assets like images, JavaScript files, and style sheets, so they don't need to be re-downloaded on every page visit. Number four, database cache. Many database systems have their own internal caching mechanisms. Database caching involves storing frequently queried database results in an internal cache. This reduces the number of times the database has to execute the same expensive queries, improving its performance and scalability. Lastly, content delivery network. A CDN is a geographically distributed network of proxy servers. CDNs are used to store copies of static content like images, videos, and web pages on server located in different geographic locations around the world. This is significantly reduced latency by serving content to users from a server that is physically closer to them. Okay, next, we'll talk about some caching strategies. We'll talk about read-through cache. In this strategy, the application first checks the cache for the data it needs. If the data isn't there, we call this a cache miss. The cache itself is responsible for retrieving the data from the underlying database, updating its own storage, and then returning it to the application. The application talks only to the cache. Next, we have write-through cache. When data is written, it's written to both cache and the database simultaneously. This ensures that the cache and the database are always constant, which is great for data integrity, but it can potentially impact the write performance because you're doing 2 writes for every operation. Number 3, we have write back cache or write behind. With write back, data is written to the cache first, and the write to the database happens later, often in patches or after a delay. This is significantly improves write performance from the application's perspective, but introduces a risk of data loss if the data fails before the data is synchronized to database. Lastly, we have cache aside or lazy loading. This is a very common strategy where the application code itself is responsible for managing both the cache and database. When reading, the application first checks the cache. If it misses, the application reads from the database, then manually populates the cache with the data before using it. When writing, the application typically writes directly to database and then often invalidates or updates the corresponding entry in the cache. Next, we will talk about cache eviction policies. Like caches have limited storage space. So what happens when the cache gets full and new data needs to be stored? This is where cache eviction policies come in. These policies determine which existing data items should be removed to make room. First, we have least recently used, or LRU. Basically, least recently used is a very popular policy. It evicts the data that was accessed least recently when the cache is full. The underlying assumption is that data which hasn't been used in a while is less likely to be needed again. Number two, we have least frequently used, or LFU. LFU evicts the data that has been accessed the least number of times, regardless of when it was last accessed. The idea here is that really accessed data is less important to keep in the cache. Number three, first in, first out. As the name suggests, first in, first out evicts the oldest data is in the cache first, irrespective of how often or how recently it has been accessed. It is simple, but not always the most efficient. Number four, time to live, or TTL. TTL isn't strictly an eviction policy for when the cache is full, but rather than a time-based mechanism. Data is removed from the cache after specified duration has passed since it was added, regardless of its usage. This is great for data that becomes stale after a certain period. Okay, we will talk about some challenges and considerations. Basically, what to watch for, what to watch out for. So while caching is powerful, it's also introduced its own set of complexities and challenges. The first thing we have cache consistency. Okay, and this is a big one. You need to ensure that the data stored in your cache remains consistent with the data in your primary data store, which is a source of truth like your database. If the database gets uploaded but the cache doesn't, users might see stale data or incorrect data. Next, we have cache invalidation. This is closely related to coherence. It's about determining when and how to update or remove stale data from the cache to prevent users from seeing outdated information. This can be surprisingly tricky to get right. Number three, cold start. What happens when your system restarts and the cache is initially empty? This is known as cold start. The initial requests will be a cache misses, potentially overwhelming your backend systems until the cache warms up. Number four, cache eviction policies. Again, deciding which items to remove when the cache reaches its capacity, like LRU or LFU, is LFU, not U. Basically, is crucial for maintaining cache effectiveness. The wrong policy can lead to frequently needed data behind being evicted too soon. Number five, cache penetration. This is a security and performance concern. It occurs when malicious actors or just buggy code repeatedly query for data that doesn't exist and will never exist in the cache for the database. Each miss goes to the backend, potentially overwhelming it. Lastly, cache stampede. Um, I always pronounce, I guess, stampede.
Stampede.
Yes, cache stampede. Sorry. So lastly, we have cache stampede. This happens when a popular cached item expires and many concurrent requests all try to access it at the same time. All these requests result in cache misses and simultaneously try to rebuild that cache entry by hitting the database again, potentially overwhelming the backend. Okay. Next, we have best practices for implementing cache effectively. First, cache the right data. Don't just cache everything. Focus on caching data that is quite expensive to query, and it's not that easy to generate or slow to retrieve from the backend, and critically data that is frequently accessed. Number two, set appropriate time to live. Use time to live strategically to automatically invalidate cache entries and help prevent users from seeing stale data. The duration should match how quickly your data is changed. Number three, consider cache warming. For critical or very frequently accessed data, preload it into the cache during application startup or off-peak hours to avoid the initial cold start performance hit. Number four, monitor cache performance. Regularly monitor key metrics like cache hit miss ratios, cache latency, and eviction rates. Use these insights to adjust your caching strategies and eviction policies based on actual usage patterns. Number five, use layer caching. Often the most effective approach is to implement caching at multiple layers. For example, client-side browser caching, CDN caching, server-side in-memory caching as well, and even database caching to minimize the performance benefits. So yeah, you need to use a lot of layers of caching. Lastly, handle cache misses gracefully. Design your system to handle cache misses effectively and efficiently without causing significant performance degradation or cascading failures. The backend should be able to cope if if the cache isn't there. Okay, I guess we reached at the end. So caching is undeniably a powerful and indispensable technique in modern system design. When implemented correctly, it can drastically improve the performance, scalability, and cost efficiency of almost any system. However, as we have seen, it comes with its own set of challenges, particularly around maintaining data consistency and managing cache invalidation. By understanding different types of caches and the various placement strategies, eviction policies, and adhering the best practices, you can design a robust, highly effective caching strategy that truly meets the needs of your application and delights your users with speed. So that's it for this video, and see you guys in the future.